Chapter 9. Bases and relations of electric units. Effects of an electric current. Three things must coexist in an electric circuit: electromotive force, current, and resistance. The effects of an electric current depend upon the rate of electric quantity which constitutes it. If any two of the above are known, the other can be determined by Ohm's law. Two systems of CGS electric units. There are two systems of electric units of the CGS system. They are termed absolute units. One is the absolute system of electrostatic units. The other is the absolute system of electromagnetic units. The basis of practical units. The absolute electromagnetic units are usually assumed to be the basis of the practical units such as the volt and ampere, although the latter could be derived from the electrostatic units, the basis for measurement and definition of a current. If a current passes through a conductor, it produces various effects. These effects, by their intensity, give a basis for measuring and defining the intensity of the current. One of these effects is the production of a field of force. A magnet pole is acted on by a field of force. It is attracted or repelled by a current. As the effect diminishes rapidly with the distance intervening between current and magnet, the effect is practically limited in extent to a small volume of space. The volume within which the effect is discernible is called a field of force. Theoretically, a field of force may be as large as the universe. Practically, artificial fields of force are small in volume. The field of force of the field magnet of a bipolar dynamo is little more in extent than the volume existing between its pole faces. The intensity of a field of force can be measured by its action on a magnet pole of known strength. A unit magnet pole is one of such strength that it will attract or repel another unit pole at a distance of 1 centimeter with a force of 1 dyne. The absolute CGS electromagnetic unit of current. The absolute CGS unit of current is the following. It is the intensity of a current which, passing through a conductor 1 centimeter long, bent into the arc of a circle of 1 centimeter radius, will attract or repel with a force of 1 dyne a unit magnet pole placed at the center of such circle. The diagram shows an arc of this radius with its center indicated. Calling the force F, we have, for the case described, F equals 1. This is equation 1. Suppose that the current goes through a complete circle of 1 centimeter radius. Its action on a magnet pole at its center will be greater than in the last case in the ratio of the lengths of the conductors. A circle of radius 1 has a length or circumference of 2 pi. The ratio of the arc of the first case to that of the circle of the second case is 1 to 2 pi. Therefore, as these are the lengths of the conductors acting on the magnet pole, and as the intervening distance is the same in both cases, the force acting on the magnet is expressed by F equals 2 pi. This is equation 2. Example. With what force will a unit magnet pole at the center of a circular conductor, the circle into which it is bent being of 1 centimeter radius, be acted on when a unit current passes? Solution. Substituting for pi in equation 2 its value 3.1416, we have for the force F equals 2 pi equals 2 times 3.1416, which equals 6.2832 dynes. Continuing, the variation of force with radius, turns, and current strength. Suppose the wire is bent into a circle of radius r. The length of the conductor is now 2 pi r, and as far as this change of length is concerned, its action on the pole at its center varies directly with that length. But the distance from the pole also increases with r, and since radiant action varies inversely with the square of the distance, we must account for both. So the direct effect from increased conductor length scales with r. The weakening from distance scales with 1 over r squared. Combining these, the force becomes F equals 2 pi r divided by r squared, which simplifies to 2 pi over r. This is equation 3. Example. Assume the radius of a conductor bent into a circle to be 7 centimeters. With what force will a unit current passing through it act upon a unit pole at its center? Solution. Substituting the values into equation 3, F equals 2 times 3.1416, which is 6.2832, divided by 7, equals 0.8976 dyne. Now extending this further, suppose the circular conductor is wound around the circle a number of times, say n turns. It then acts with n times the effect of a single loop. Equation 3 now becomes F equals 2 pi n divided by r. That's equation 4. Now, if the current, instead of being unit current, is some current of strength I, the equation becomes F equals 2 pi n I over r. This is equation 5. Solving for I gives I equals Fr over 2 pi n. That is equation 6. Now finally, if the magnet pole has strength m, then the force will be m times greater. This is because the force between the current and the pole depends on both their strengths. It is a product of two effects. So equations 5 and 6 for a magnet pole of strength m become F equals 2 pi n I m over r. That is equation 7. And solving for current I, we get I equals Fr over 2 pi n m. That is equation 8. To answer example, a magnet pole of 5 unit strength at the center of a circle of 11 centimeters radius composed of 24 turns of wire is acted on by a force of 377 dynes. What is the intensity of current passing through the wire? Solution. By substituting in formula 8, we obtain I equals 377 times 11 divided by 6.2832 times 24 times 5, which equals 5.5 CGS units. The tangent compass. If in the center of such a coil a very short compass needle is established, a tangent compass is produced. The compass needle is acted on by the horizontal component of the Earth's magnetic field. The circle of the galvanometer is placed in the magnetic meridian approximately north and south. A current passing through the wire tends to deflect the needle into a position at right angles to the plane of the coil. This is at right angles to the position in which the Earth's component tends to keep it. Action of Earth's field. The Earth's field acts upon the needle with the product of the horizontal component of the Earth's magnetism by the strength of the magnet. This product we may call HM, where H represents the horizontal component of the Earth's magnetism, and M is the force of the magnet. Angle of divergence. At a given angle of divergence, theta, from the magnetic meridian, the lever arm of the Earth's action on the magnet is equal to the product of the magnet's length by the sine of the angle of divergence. This is shown in the diagram. The Earth acts upon both arms of the magnet with virtual lever arms of length AB, and the sum of the two is as if it acted upon the magnet with a single lever arm equal to the length of the magnet multiplied by sine theta. By the same course of reasoning, we find that the coil acts with a lever arm equal to the product of the magnet's length by the cosine of the angle of divergence. Combined action of coil and Earth's field on magnet. Calling the length of the magnet L, we have for the Earth's action, HML sine theta. And for the action of the coil, 2 pi ni ml cosine theta, that is, 2 pi times n times I times m times L times cosine theta. In any position of equilibrium which the needle assumes, it will be acted on equally by these two opposing forces. They therefore may be made equal to each other. So 2 pi ni ml cosine theta over r equals HML sine theta. This is equation 9. In this expression, m and l cancel out, and by transposition the formula becomes I equals r divided by 2 pi n times h times sine theta over cosine theta, or more simply, I equals rh tangent theta over 2 pi n. That is equation 10. Tangent galvanometer formula. This is the formula of the tangent galvanometer, developed here at length to show how the electromagnetic CGS unit of current can be directly determined. It will be observed that the only constant entering into the formula is the horizontal component of the Earth's magnetism. This has been determined for a great many places. Example, the radius of a coil is 30 centimeters, the number of turns is 5, the value of H is 0.1590 dyne, and the needle is deflected by a current passing through the coil to an angle of 50 degrees in 11 minutes. Calculate the current strength in CGS units. Solution. Substituting in equation 10, we have I equals 30 times 0.1590 divided by 6.2832 times 5 times tangent of 50 degrees 11 minutes, which is approximately 1.2, equals 0.18 CGS unit of current. Determining CGS units of EMF and resistance. It now remains to be shown how the CGS units of electromotive force and of resistance are found. The energy due to an electric discharge is equal to the product of the quantity discharged by the potential difference of the points or places between which the discharge takes place. The ergs per second of energy expended when a current of electricity is passing through a conductor is equal to the current strength multiplied by the EMF required to maintain the current through the conductor in question. The energy expended is converted into heat energy. All units are assumed as of the CGS system. By placing a conductor in a calorimeter, passing a known current through it, the current being taken in CGS units, determining the ergs per second produced, the EMF expended on the conductor is manifestly equal to the ergs divided by the current, because the current is numerically equal to the quantity per second. Then, having the current and EMF, the resistance of the conductor is calculated by Ohm's law. Example, a current of 0.114 units passing through a calorimeter wire for 1 minute produces 40 calories of heat. Calculate the EMF between the terminals of the wire and the resistance of the wire. Solution. To reduce the calories to ergs, they must be multiplied by 416.7 times 10 to the fifth, whence the ergs per minute corresponding to the calories of the problem are 40 times 416.7 times 10 to the fifth, which equals 1,666.7 times 10 to the sixth ergs, or 1,666,70,00 ergs. Dividing the ergs per minute by 60 gives ergs per second. 1.667 times 10 to the sixth divided by 60 equals 278 times 10 to the fifth ergs per second. This is to be divided by the quantity of electricity per second, which is numerically equal to the current. 278 times 10 to the fifth divided by 0.114 equals 243 times 10 to the sixth CGS units of EMF. The resistance of the wire is calculated by Ohm's law. R equals E divided by I, whence 243 times 10 to the sixth divided by 0.114 equals 213 times 10 to the seventh CGS units of resistance. 1 CGS unit of current equals 10 amperes. The current therefore is 0.114 times 10 equals 1.14 amperes. 10 to the eighth CGS units of E diam F equals 1 volt. The EMF therefore is 2243 times 10 to the sixth divided by 10 to the eighth equals 2.43 volts. 10 to the ninth CGS units of resistance equals 1 ohm. The resistance therefore is 213 times 10 to the seventh divided by 10 to the ninth equals 2.14 0.13 ohms. This section is designed to show the relation of the absolute units to the practical ones, and also the relation of the apparently abstract bases of the absolute system to the standards of the engineer. It is not to be taken as showing approved details of making these determinations, which exact the most accurate work and refinement in methods. An ammeter and a voltmeter could be standardized or calibrated by the above method. The length, diameter, and material of a wire of 1 ohm resistance could be determined, and with these bases, the other practical units could be determined and standards fixed for them. The absolute CGS electrostatic unit of quantity. The absolute electrostatic unit of quantity is that quantity which would attract or repel a similar quantity 1 centimeter distant with a force of 1 dyne. From this as a basis, a full series of units of the ES system, as the term may be conveniently abbreviated, is deduced. Determination of the ES unit of potential. To obtain an experimental basis, we may start with the determination of potential difference. The attracted disk electrometer can be used for this determination. The attracted disk electrometer. It comprises a disk held above and parallel to a plate, the plate being much larger than the disk. The apparatus is so arranged that the attraction between plate and disk and the distance separating them can be determined. In the diagram, the disk is represented by the line S, the plate by the line T, and an annular plate surrounding the disk, as close to it as possible, is also indicated. By touching one of the two, disk or plate, with an excited conductor, a charge is imparted, and they attract each other. Call the surface density of the charge plus for one surface and minus for the other. The attraction of an indefinitely large plane with a surface density sigma for a point, in this case a unit of quantity, placed opposite its center is 2 pi sigma. This is the attraction of the plate for a unit of quantity of electricity on the disk. Surface density is the quantity of electricity per unit area of the plate or disk. Call the area of the disk capital S. Then the entire quantity on its surface is sigma times S. It will be seen that sigma represents the quantity on a unit area of the disk, because the surface densities of the charges on plate and disk are identical. The attraction A between disk and plate is therefore A equals 2 pi sigma times sigma S, which equals 2 pi S sigma squared. This is equation 1. Because sigma S is numerically equal to the number of units of quantity on the disk, transposing equation 1 gives sigma squared equals A over 2 pi S. This is equation 2. If a point is situated between the disk and plate, both will act, one attracting and the other repelling any mass between them, and hence both exercising force in the same direction. The force at such a point will be the force exercised by one of the surfaces multiplied by 2. So 2 pi sigma times 2 equals 4 pi sigma. If a unit quantity is transferred from one plane to the other, as from disk to plate, the energy involved is numerically equal to the difference of potential between the two surfaces. This is because the product of potential difference by quantity is energy. And as the quantity transferred is supposed to be equal to unity, the potential difference and the energy have the same numerical value. Call the potential difference between the two surfaces capital P and the distance between the plates lowercase d. Then the potential difference will be equal to the force, 4 pi sigma, exercised on a unit of quantity multiplied by the distance of transfer d, giving P equal 4 pi sigma d. This is equation 3. Substituting for sigma from equation 2, we have P equals 4 pi d times the square root of A over 2 pi S, which simplifies to P equals d times the square root of 8 pi A over S. This is equation 4. The force of attraction A is measured. The area of the disk S and the distance d are known. Substituting for A, S, and d their values, the numerical value in electrostatic units of the potential difference between the plate and disk is found. In carrying out this calculation, CGS units must be used. The force of attraction must be expressed in dynes. Example: in an attracted disk electrometer, the area of the disk was 10 square centimeters. The distance from the disk to the plate was 0.5 centimeters. After imparting a charge to the disk, the attraction was 0.092 grams. Calculate the potential difference in electrostatic CGS units. Solution. Substituting for the symbols of the formula, that is, equation 4, their values, it becomes P equals 0.5 times the square root of 8 pi times the product of 0.092 times 981 divided by 10 equals 7.53 electrostatic units. The part of the expression in parentheses, 0.092 times 981, is the force of attraction in dynes, on the assumption that the force of gravity was measured by an acceleration of 981 centimeters per second squared. It is equal to 90.252 dynes. Other units of the electrostatic system. If one such unit of electromotive force were expended on maintaining a current of such strength that the two would expend 1 erg of energy per second, the current would be of 1 electrostatic absolute unit strength. The resistance of the conductor through which this current would be forced by a unit of potential difference would be 1 electrostatic unit in amount. From this basis, the whole series of electrostatic units can be deduced. The EM and ES systems of units. The value of a current or of potential difference may be determined in absolute units by various methods which give it directly. Examples of such are given in the preceding pages, where they are employed simply to give the concrete idea of what these units are, of how they are related to the 3 fundamental units of time, space, and mass, and of how they can be determined experimentally by direct use of the centimeter, gram, and second. One set of electric units is based on the attraction of oppositely charged surfaces for each other, or, what is the same thing, on the repulsion of similarly charged ones. This set of units is called the electrostatic series. Another series is based on the action of an electric current on a magnet pole. This series is known as the electromagnetic series. Both sets of units are CGS units and can be used for electric specification and calculation, one just as well as the other. The units of the two systems have values which differ from the values of corresponding units of the other system. The relation of the values has been determined by experiment, and the results are very accurate, yet not absolutely so. The EM absolute unit of quantity is equal to 3 times 10 to the 10th ES units. The coulomb is equal to 10 to the negative 1 EM absolute units, and therefore is equal to 3 times 10 to the 9th ES units. Exactly the same relations exist for the current units, so that the ampere is equal to 3 times 10 to the 9th ES units. The ES unit of potential is equal to 3 times 10 to the 10th EM absolute units. The volt is equal to 10 to the 8th EM absolute units, and therefore is equal to 1/3 times 10 to the negative 2nd ES unit. The ES unit of resistance is equal to 9 times 10 to the 20th EM absolute units. The ohm is equal to 10 to the 9th EM absolute units, and therefore is equal to 1/9 times 10 to the negative 11th ES unit. The EM absolute unit of capacity is equal to 9 times 10 to the 20th ES units. The practical unit of capacity, the farad, is equal to 10 to the negative 6th EM absolute units, and therefore is equal to 9 times 10 to the 11th ES units. The subject of capacity is treated of in Chapter 15. Derivation of practical units from absolute units. From absolute units, the practical units are derived from the absolute units by either of two methods, each giving an identical result. The simplest method is to reduce the units of the absolute series to those of the practical series by multiplying by defined factors. The table gives the value of the units of the practical series in terms of the absolute units with the factors. The factors are all powers of 10 or multiples thereof. The practical units are defined as follows. Absolute units. The relations of absolute units are given as follows. 1 unit of quantity in electromagnetic absolute units is 3 multiplied by 10 raised to the power of 10. 1 electrostatic unit of quantity is 1/3 multiplied by 10 raised to the power of negative 10. 1 unit of current in electromagnetic absolute units is 3 multiplied by 10 raised to the power of 10. 1 electrostatic unit of current is 1/3 multiplied by 10 raised to the power of negative 10. 1 unit of capacity in electromagnetic absolute units is 9 multiplied by 10 raised to the power of 20. 1 electrostatic unit of capacity is 1/9 multiplied by 10 raised to the power of negative 20. 1 unit of potential in electromagnetic absolute units is 3 multiplied by 10 raised to the power of negative 10. 1 electrostatic unit of potential is 3 multiplied by 10 raised to the power of 10. 1 unit of resistance in electromagnetic absolute units is 1 multiplied by 10 raised to the power of negative 20. 1 electrostatic unit of resistance is 9 multiplied by 10 raised to the power of 20. There are slight mistakes in the way the table is read, but by looking at the data on screen, they are easily found. Example, calculate the equivalent of 5 volts in electrostatic units, absolute. Solution, a volt is equal to 10 raised to the power of 8 absolute electromagnetic units. Therefore, 5 volts are equal to 5 multiplied by 10 raised to the power of 8 absolute electromagnetic units. For the equivalent electrostatic units, this must be divided by 3 multiplied by 10 raised to the power of 10. 5 multiplied by 10 raised to the power of 8 divided by 3 multiplied by 10 raised to the power of 10 equals 5 divided by 3 multiplied by 10 raised to the power of negative 2, which equals 0.0166 electrostatic units. Alternatively, using the table, 5 multiplied by 10 raised to the power of negative 2 equals 0.0166 electrostatic units. Example, what is the value of 1 volt in absolute electrostatic units? Solution, from the above calculation, it follows that the value of 1 volt is 0.0166 divided by 5 equals 0.0033 electrostatic units. Alternatively, using the table, 1 multiplied by 1/3 divided by 10 raised to the power of negative 2 equals 0.0033 electrostatic units. Example, what is the value of 28.3 electrostatic absolute units in volts? Solution, as the electromagnetic unit is equal to the electrostatic unit divided by 3 multiplied by 10 raised to the power of 10, the reverse rule holds. The electrostatic unit is equal to the electromagnetic unit multiplied by 3 multiplied by 10 raised to the power of 10. 28.3 multiplied by 3 multiplied by 10 raised to the power of 10 equals 849 multiplied by 10 raised to the power of 9 absolute electromagnetic units. To reduce this to volts, divide by the equivalent of the volt in absolute electromagnetic units, which is 10 raised to the power of 8. 849 multiplied by 10 raised to the power of 9 divided by 10 raised to the power of 8 equals 8,490 volts. Alternatively, using the table, 28.3 multiplied by 3 multiplied by 10 raised to the power of 2 equals 8,490 volts. Example, an electromotive force of 120 volts produces a current of 5 amperes. Reduce these quantities to electrostatic absolute units. Apply Ohm's law to the result, obtaining the value of the resistance in the same system of units. Then, reduce the resistance thus calculated to ohms and test the correctness of the operation by Ohm's law applied directly. Solution. The absolute value of 120 volts in the electromagnetic system is 120 multiplied by 10 raised to the power of 8, which equals 12 multiplied by 10 raised to the power of 9. Applying the equivalent to obtain the value of this quantity in absolute electrostatic units gives 12 multiplied by 10 raised to the power of 9 divided by 3 multiplied by 10 raised to the power of 10 equals 4 multiplied by 10 raised to the power of -1 electrostatic units. 5 amperes are equal to 5 multiplied by 10 raised to the power of -1 absolute electromagnetic units. Applying the equivalent gives 5 multiplied by 10 raised to the power of -1 multiplied by 3 multiplied by 10 raised to the power of 10 equals 15 multiplied by 10 raised to the power of 9, which is the current in electrostatic units. Applying Ohm's law to the electrostatic units determined above gives 4 multiplied by 10 raised to the power of -1 divided by 15 multiplied by 10 raised to the power of 9 equals 266 multiplied by 10 raised to the power of -13, which is the resistance in electrostatic units. To test the correctness of the operation, proceed as follows. The original data gives the resistance by Ohm's law as 120 divided by 5, which equals 24 ohms. 24 ohms is equal to 24 multiplied by 10 raised to the power of 9 absolute electromagnetic units. Applying the equivalent gives 24 multiplied by 10 raised to the power of 9 divided by 9 multiplied by 10 raised to the power of 20 equals 266 multiplied by 10 raised to the power of 13, as found by the previous operation. This proves the correctness of the calculation. This example is given only as an exercise. The results are more easily obtained using the tables. The practical units of the electromagnetic system can be directly derived from the dimensional formulas of units by changing the units of length and mass. Let the unit of mass be 10 raised to the power of -3 grams, and the unit of length be 10 raised to the power of 9 centimeters, with the unit of time being the second, as in the absolute system. If these values are introduced into the electromagnetic dimensional formulas, the resulting units will correspond to the practical system: volts, amperes, ohms, and other regular engineering units. Calculate the value of the ampere in absolute electromagnetic units. An error crept in again, so starting from the previous paragraph again. Let the unit of mass be 10 raised to the power of -11 grams, and let the unit of length be 10 raised to the power of 9 centimeters, with the unit of time being the second, as in the absolute system. If these are introduced into the electromagnetic dimensional formulas of units, the resulting units will correspond to the practical system: volts, amperes, ohms, and other regular engineering units. Solution. The dimensions of the unit are mass to the 1/2 power, length to the 1/2 power, and time to the power of -1. Substituting for these symbols their values as given above, we have for the ampere, 10 raised to the power of -11 over 2, multiplied by 10 raised to the power of 9 over 2, multiplied by time raised to the power of -1, equals 1 multiplied by 10 raised to the power of -1 CGS units. 10 amperes are equal to 1 absolute electromagnetic unit. Example, calculate the value of the ohm and volt as above. Solution. For the ohm, the dimensions are length multiplied by time raised to the power of -1. For the volt, the dimensions are mass raised to the 1/2 power, length raised to the 9 over 2 power, and time raised to the power of -2. For the ohm, 10 raised to the power of 9 multiplied by 1 raised to the power of -1 equals 10 raised to the power of 9 CGS units. For the volt, 10 raised to the power of -11 over 2 multiplied by 10 raised to the power of 27 over 2 multiplied by 1 raised to the power of -1 equals 10 raised to the power of 8 CGS units. The value of the reduction factor of the two systems of CGS units, which is also the numerical value of the velocity of light in centimeters, is approximately 3 multiplied by 10 raised to the power of 10. This value applies to the electromagnetic theory of light. The reduction factor has been determined with close approximation to the exact figure by several investigators, with results that are reasonably concordant. The following are some of the results reached by recent observers. In 1883, J.J. Thomson found 2.963 multiplied by 10 raised to the power of 10. In 1889, Lord Kelvin 3.004 multiplied by 10 raised to the power of 10. In 1890, J.J. Thomson and G.F.C. Searle calculated 2.9955 multiplied by 10 raised to the power of 10. Later, O. Lodge and Glazebrook found 3.009 multiplied by 10 raised to the power of 10. Example. Calculate the dimensions of the reduction factor to reduce the electrostatic unit of capacity to the electromagnetic unit. Solution. The dimensions of the electrostatic unit are length. The dimensions of the electromagnetic unit are length raised to the power of -1 multiplied by time squared. To find the factor, divide the second by the first. Length raised to the power of -1 multiplied by time squared divided by length equals length raised to the power of -2 multiplied by time squared. This is the reciprocal of velocity squared. Example. Make the same calculation for current units. The dimensions of the electrostatic unit are mass multiplied by length multiplied by time raised to the power of -2. The dimensions of the electromagnetic unit are mass multiplied by length multiplied by time raised to the power of -1. Dividing the electromagnetic dimensions by the electrostatic dimensions gives mass multiplied by length multiplied by time raised to the power of -2 divided by mass multiplied by length multiplied by time raised to the power of -1 equals length multiplied by time raised to the power of -1, which are the dimensions of velocity. Dimensions of electromagnetic quantities. Two magnetic poles of equal strength and opposite polarity attract each other. This attraction is directly proportional to the square of the quantity of magnetism in one of the poles, and inversely proportional to the square of the distance between them. Dimensions of magnetic quantity. Let the quantity of magnetism in each pole be represented by Q, and let the distance between the poles be L. The attraction between the poles is a force, and the dimensions of force are mass multiplied by length multiplied by time raised to the power of -2. For this specific case, force is proportional to Q text squared divided by L squared. Equating these expressions, we write the quantity of magnetism squared multiplied by the reciprocal of length squared equals mass multiplied by length multiplied by time raised to the power of -2. Solving for Q text squared, we find the quantity of magnetism squared equals mass multiplied by length raised to the power of 3 multiplied by time raised to the power of -2. Taking the square root, the dimensions of Q are mass raised to the power of 1/2, length raised to the power of 3/2, and time raised to the power of -1. Dimensions of current in the electromagnetic system. Let I represent the strength of a current passing through a conductor of length L. Assume the conductor is bent into the arc of a circle with radius L. Place a magnetic pole representing a quantity of magnetism Q at the center of the circle. The force between the current and the magnetic pole depends on three factors. 1. The strength of the current. 2. The length of the conductor. 3. The quantity of magnetism. The force is proportional to the product of the current strength, the length of the conductor, and the quantity of magnetism divided by the square of the distance between them. Substituting L for the distance, this simplifies to force is proportional to the current multiplied by the quantity of magnetism divided by the conductor length. The force also has the dimensions of mass multiplied by length multiplied by time raised to the power of -2. Equating the two expressions, we write current multiplied by the quantity of magnetism multiplied by the reciprocal of length equals mass multiplied by length multiplied by time raised to the power of -2. Substituting the dimensions of magnetic quantity, which are mass to the power of 1/2, length raised to the power of 3/2, and time raised to the power of -1, we find current. Current multiplied by mass to the power of 1/2 multiplied by length to the power of 1/2 multiplied by time raised to the power of -1 equals mass multiplied by length multiplied by time raised to the power of -2. Finally, solving for current, the dimensions are mass raised to the power of 1/2, length raised to the power of 1/2, and time raised to the power of -1.